Hi everyone, my name is Rahma from Chemistry Extensive Channel. I'm experienced in university, college and secondary school chemistry teaching. On this channel, we discuss organic chemistry, medicinal chemistry, natural product chemistry, lab works and lots more. If you are new to this channel, please do subscribe to this channel, click on the notification bell and give my video a thumb up so that you'll be the first to be notified whenever I upload new video. Today, we are going to be talking all about spectroscopy. Without a further ado, let's get started. UV spectroscopy, UV visible spectroscopy. At the end of this lesson, students should be able to explain electromagnetic radiation range of all type of radiation that has both electric and magnetic field and travel in waves. The electromagnetic spectrum is the full range of electromagnetic radiation organized by frequency or wavelength. The spectrum is divided into separate bands with different names for the electromagnetic waves within each band, from low to high frequency. These are radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, and gamma rays. The electromagnetic wave in each of these bands have different characteristics, such as how they are produced, how they interact with matter, and their practical applications. Most of the radiation that are surround us cannot be seen, but can be detected by dedicated sensing instruments. This electromagnetic spectrum range from very short wavelengths such as gamma and X-ray to a very long wavelength such as microwave and broadcast radio waves. Radiation is the energy that travels in form of wave or particles. Radiation is part of our everyday environment, from cosmic rays as well as to radioactive material found in soil, water, food, air, and also inside our body. The visible light that comes from a light lamp in your house, the radio waves that come from your radio station, the television, are examples of electromagnetic radiation. So, the types of electromagnetic radiation and its application. The radio waves is applicable in the radio and television. The microwave is applicable in the cooking, radar, telephone, and other signal. The infrared is applicable in the transmit heat from sun, fire, and radiators. Visible light is responsible for making us appreciate colors. This makes color to be able to be seen and differentiate many things. Ultraviolet is used in sterilization to kill microorganisms, observed by skin, and is used in fluorescence. Also absorbed by skin. X-ray is used inside of our body. X-ray is used to view inside of our body an object. Gamma ray is used in medicine for killing cancer cells. Electromagnetic radiation consists of waves of the electromagnetic field, which propagate through space and carry momentum and electromagnetic radiation energy. This electromagnetic wave consists of electromagnetic field, and electromagnetic radiation consists of magnetic field and electric field, which propagate through space in the same direction, carrying momentum. The wavelength in the electromagnetic field is the distance between one crest and another. The crest is the peak of each. The crest is the peak of the different wavelengths from one crest to another. The crest is the peak that's of each wave distance. And the trough is the peak below the crest. Electromagnetic fields are measured in different parameters. They are according to the fundamental measurements that are present in the electromagnetic field, which include the wavelength, the frequency, and energy. The wavelength, which can be measured in meter, centimeter, and nanometer, and the frequency, which can be measured in hertz, and energy, which can be measured in kilocal. The wavelength of electromagnetic field is gamma ray has the smallest wavelength, while the radio wave has the highest wavelength, whereas the frequency in the electromagnetic field, the gamma ray has the highest frequency, while the radio wave has the lowest frequency. The energy is perpendicular to frequency. The energy associated with the given segment of a spectrum is proportional to its frequency. The equation below describes this relationship, which provide the energy carried by photon of a given radiation. So the velocity, V representing velocity, the lambda representing wavelength, and the C representing V representing the frequency, lambda representing the wavelength, and C representing the velocity of the light. Energy equal to Planck constant multiplied by frequency. Ultraviolet radiation. The ultraviolet radiation is the portion of the electromagnetic spectrum extending from violet or short wavelength to end of the visible light range to the X-ray region. The ultraviolet radiation is undetectable by our human eyes, and many insects, however, are able to see ultraviolet radiation. The gamma ray, the X-ray, the ultraviolet is the next between the X-ray and the visible light. The ultraviolet radiation fall between visible light spectrum. The ultraviolet radiation lies between the wavelength of 400 nanometer on the visible light inside and about 10 and invisible light side, and about 10 nanometer on the X-ray side. The visible spectrum varies. The V's spectrum is the band of the electromagnetic spectrum that is visible to our human eye. Electromagnetic radiation in this range of wavelength is called the visible light, or simply light. A typical human eye will respond to wavelengths from about 380 to about 750 nanometer, where we can see different color and light. In terms of frequency, this corresponds to a band in the vicinity of 400 to 790 terahertz. These boundaries have not sharply defined and may vary per individual. Under optimal conditions, this limit of human perception can extend 310 nanometer ultraviolet and 1100 nanometer near infrared. Introduction of the UV-V spectroscopy. The UV-V spectroscopy, the UV-V spectrum is a UV visible wavelength region at which most molecules absorb light that are visible to human eye. A typical human eye will respond to wavelength from about 380 to about 750 nanometer, which fall between ultraviolet and visible light. The ultraviolet, the UV-Vs, is representing the UV-Vs, which is about 380 here, to about to almost 750, close to the infrared region. And this region is the region where it is possible for humanly eye to see different color and light. An obvious difference between certain compounds is their color. You will agree with me with that different compounds have different color depending on their conjugate bond. Thus, quinone is yellow, chlorophyll is green, and 2,4-dinitrophenylhydrazone of derivative of aldehyde and ketone range from yellow to deep red, depending on double bond conjugate, and aspirin is said to be colorless. In this respect, the human eye is functioning as a spectrometer. In this respect, the human eye is functioning as spectrometer, analyzing the light reflected from the surface of a solid or passing through a liquid. This is a question to be treated. A carrot looks orange in color because of the beta-carotene molecule in it. This means that the beta-carotene molecule absorbs light of wavelength of at dash. The answer to it is that the approximately value of wavelength for orange color is between 590 to 625. Hence, for carrots having orange color, beta-carotene molecule absorb wavelength longer than 550 and shorter than 700. Function of prism when light passes through it. Although we see sunlight or we see white light as uniform of homogeneous in color, while it actually possesses of broad range of radiation wavelength in the ultraviolet region, visible and infrared portion of the spectrum. Looking at this diagram, when light passes through a prism, there will be a diffraction which will separate different color from their visible light, showing that the visible light is having different color absorbed in it. As shown in the diagram, the component color of the visible portion can be separated by passing sunlight through a prism, which acts to bend the light in differing degree according to wavelength. White light passes through the prism. There's a diffraction of the light which gives different color of red, orange, yellow, green, blue, indigo, and violet. The movement of light in UV spectroscopy, the electromagnetic radiation such as visible light is commonly treated as a wave phenomenon characterized by a wavelength or frequency. So the wavelength is defined in the diagram above as the distance between adjacent peak or trough, and may be designated in meters, centimeter, and nanometer. Frequency is the number of wave cycles that travel past a fixed point per unit of time and is usually given in cycle per second or hertz. Visible wavelengths cover a range from approximately 400 to 800. And as we can see here, as the frequency, this is an example of high frequency, and this is an example of low frequency. So when we have low frequency, we will have high wavelength. When we have high frequency, we will have low wavelength. So frequency is equal to the number of oscillations per second. So this is the formula that is representing the frequency. This is the formula representing the velocity and frequency. Velocity equal to frequency multiplied by lambda, and frequency frequency is inversely proportional to wavelength. The longest visible wavelength is red and the shortest is violet. Other common color of spectrum in order of decreasing wavelength may be remembered by the mnemonic Roy G. Beef. Each R representing red, O representing the orange, yellow, green, and B representing blue, I representing indigo, V representing violet. The wavelength is representing with different wave spectrometer. The wavelength is representing with different wave color. Violet has the wavelength of 4 to 420, indigo 20 to 440, blue 40 to 490, green around 490 to 570, yellow around 570 to 585, orange around 585 to 620, red around 620 to 780. the wavelength of what we perceive as a particular color in this visible portion of a spectrum are displayed below. So our eyes are able to see color within the range of this visible light. Wavelength will increase on moving from left to right. From the diagram below, from moving from UV 400 to infrared 180. So the wavelength move across this. So a common feature of this color compound displayed below is a system of extensive conjugated pi electron. Some natural organic pigments include alizarin, and which is found in mother root, and also casmesic acid, which is found in Cactus cacti, indigo, which is also found in which is found in wood, and also crocetine, which is found in saffron, and also the carotene, which is found in carrot, which is all this has different pigments, and carotene has orange color. Ultraviolet visible spectroscopy, or UV-vis, is an analytical technique that measures the amount of discrete wavelength of UV or visible light that are absorbed by or transmitted through a sample in comparison to reference or blank sample. The UV range from UV to near infrared. So at this region, the probability of seeing color for human eye is possible from around 380 to around 750. The ultraviolet visible spectroscopy, to understand why some compounds are colored and others are not, and to determine this relationship of conjugation to color, we must make accurate measurements of light absorption at different wavelengths in and near the visible part of spectrum. The commercial optical spectrometer enables such experiments to be conducted with ease and under survey both the near ultraviolet and visible portion of spectrum. The visible spectroscopy instrumentation. In absorption spectroscopy, we measure energy as a function of wavelength. The instrument we use to do this is called a UV visible spectrometer. It's called a UV visible spectrophotometer. The major components are a light source, a monochromator, a sample compartment, a detector, and recorder. A monochromator in UV spectrophotometer spectrophotometer work as this. A monochromatic UV A monochromatic UV spectrophotometer works as this. The light source hits the collimator lens, which is the monochromator, which this hits the diffraction graphite or prism, and this transfer wavelength. This transfers the diffracted light to the wavelength selector slit. The selector slit then pass the incident light to the solution. The solution tends to absorb the light, and the light which could not be absorbed by the solution tend to hit the detector, which we read as the color, which we see as the color of the compound. The UV spectrophotometer is an analytical instrument that measures the amount of ultraviolet and visible light that is absorbed by a sample. So the same principle goes with this. UV visible spectroscopy light source can be from xenon. Xenon can be in form of light, in form of lamp or flash. The xenon arc lamp produces a bright light that is similar to natural sunlight through ionization of xenon gas atom under high pressure. The xenon flash lamp are a more compact version of xenon lamp that generate less heat by emitting light in short pulse rather than continuously. Pure xenon has a very wide emission spectrum between around 200 to 120 nanometer higher intensity than halogen lamp. Xenon is blue shifted for more power in the UV region, used more often for sterilization. Another type of light source is deuterium. So deuterium gas is discharged. Deuterium has a spectrum between 180 to 370. The UV spectrophotometer also can have source light by using halogen lamp, which range between 350 nanometer to 3500 nanometer. The mercury lamp is another type of lamp which can be used in the UV range. Monochromator is another compartment of the spectrophotometer. The light source we use produce continuous emission spectra. So in the monochromator, this is called the Crazy tonal setup. The B and C setup, a beam that is at indefinite focus. The D is either a prism or a diffraction grating, almost always the latter these days. The E refocus one wavelength on slit F. and the different wavelengths can be focused on F by rotating D or E, and most time we rotate D. Sample compartment is another component in the spectrophotometer. The sample itself is held in the cuvette, usually plastic or quartz, like this. So this is where the sample will be held and it will be read from the spectrophotometer. The detector can be silicon iodide, or it can be silicon iodide, or it can be photo multiplier. The whole instrument includes this: the light source, the crazy toner, the sample, the design can include, the whole instrument can include the light source, the designing toner, sample, detector, and this is the overall